The last rule of 1.5 is what we call the sum and difference rule, and basically it states how do we take the derivative of a sum or difference of two functions. And much like limits, it's quite simple. Basically, if you have the derivative of a sum of two things, you can take the derivative of each part separately. Same goes for difference. We'll go ahead and skip the proof in the difference quotient, but the proof is pretty simple to do by using the definition of the derivative, since the definition of the derivative involves the limit of the difference quotient. Basically, if you take the limit of a difference quotient of a sum, you can split the limit into two parts, separating f and g, which would translate to the derivative being separable as well. Let's just do a few examples and look at an application of this. So let's say I wanted to know what is the derivative of a linear function such as 6x minus 11. Well, I could take the derivative of each part separately. So I could do d dx of 6x minus d dx of 11. And then I could use all the other rules that we've been working on to say, well, the 6 will not affect this derivative, and the derivative of x is 1. So 6 times 1 is 6. And the derivative of a constant is always equal to 0. So I would get 6 minus 0, or 6. And what we would get for the derivative is just 6 and only 6. And again, that makes sense since it is a linear function of slope 6. It should have a constant derivative. Looking at higher degree polynomials, though, we need to make sure we're using the power rule. Again, I'm going to just skip writing this. I'm just going to differentiate piece by piece by piece. You can think of it sort of like the distributive property here, but the derivative of x cubed would be 3x squared. The derivative of 3x squared would be 6x, and the derivative of negative 9 would be 0. So I can just kind of work my way piece by piece by piece, keeping in mind all those rules that we have been working on. Let's do a few more. So, and we'll go ahead and finish the examples here from the packet, and I'll leave the try it yourselves for you to work on your own. But the derivative of 14x to the 10th, remember that the power will drop, and I need to subtract 1. So that would give me 140x to the 9th. Then with x to the 7th, the power will drop and subtract 1, so that would be minus 7x to the 6th. And with 8x to the 4th, 4 times 8 will be 32x cubed. So by power rule, I always drop the exponent and subtract 1 in order to find a derivative. And when it comes to things like fractions divided by x or roots, it is helpful to rewrite this first by using the respective exponents, fractions, negatives, and so forth. So again, if I'm not taking the derivative, I want to rewrite d dx, implying that I have not yet applied the derivative. And so I'll just start by changing them to exponentials. And remember, divided by x is the same thing as x to the minus 1 power. And the square root of x is the same as x to the 1/2 power. And now that I've rewritten those as powers, as power functions, it is much easier to take the derivative just by using the power rule. So I would have 9x squared plus 2x to the minus 2 plus 3/2 x to the negative 1/2. So in each case, I'm dropping the power, multiplying by the coefficient, and then subtracting 1 from the exponent afterwards. Or again, rewriting this more normally, 9x squared plus 2 divided by x squared plus 3 divided by 2 root x. And in each case, I would have my respective derivative. And the last thing I wanted to mention, which is a note from our packet, says, careful to understand the difference. And this is something that can be really easy to do. But remember, there's a key property with if you have a number multiplied to a function or a number added to a function. When you have a number multiplied to a function, that constant will not affect the derivative. So kind of like in this case, or in this case with 3x squared. I'm completely ignoring the 3, and I'm just taking the derivative of x squared, which is 2x. And that 2x will just multiply by 3. So the 3 will multiply right into the derivative. I can kind of, skipping is not the right word, but I can kind of ignore that for the purposes of the derivative and just take the derivative of the portion that involves x by itself. Now, when it comes to adding and subtracting, though, so that applies to multiplying and dividing. Adding and subtracting, however, if I have a function plus a constant due to the sum and difference rule, since derivatives split up piece by piece across addition and subtraction, the derivative of the function itself would, I would take each piece separately. The derivative of this would just be f prime, and the derivative of any constant is always 0. by that basic rule of derivatives. In the next video, I wanted to look at what is the importance of having a derivative equal to 0, and this is something we'll continue using as we get into applications later.